probably could have labeled this, instead of a lecture, labeled it an example problem as well. Uh, Basically, we'll try to use what we know about statistical mechanics to calculate the vibrational contribution to the specific heat. And from the previous segment, we had obtained these results. Namely, we'd gotten the total vibrational internal energy was given by this expression, where theta vibration is the characteristic vibrational temperature, and we'd found this from the partition function. And once you have that, you're really set to go. The partial derivative of the internal energy with respect to temperature at constant volume is really the heat capacity at constant volume. And generally, I don't know if you use this notation or not, but most books will use a capital C for the heat capacity. And then for the specific heat, one divides that by the number of moles present. And I usually represent that with a bar on that. I don't know if you use this notation or not, because lots of books will write this as small c, yeah, and capital C for the heat capacity, and specific heat or the heat capacity per mole over here. And I put a bar over it because if I write a small c here, I'm rapidly get my big C's and my little c's confused. But primarily, all it does is divides by the amount of substance present in terms of moles to get the molar heat capacity at constant volume. And the practical aspect for us is I don't have to carry this in around in the vibrational, the internal energy for the system. So plug this in, noting the cancellation of the number of moles. It's just a constant, so I can come outside and cancel this one here. I'm down to this. And then I didn't bring out these two, but obviously the ideal gas constant. And then for a given gas, this vibrational temperature is also a constant, so I pull those out. And at that point, we just take the derivative of everything that's in these square brackets. And the derivative of a constant is 0, so I don't even need that. So this pretty rapidly reduces to R times theta vibrational times this partial derivative of just this last term in it. And that you can use your skills from calculus to compute the partial derivative here. And the way I usually do these is I treat it like a product of two functions. The first function is this, the exponential, and then the second function is 1 over this 1 minus e to the minus theta v over t. And so I use the product rule. Yeah? And the product rule says take the derivative of the first function, which I'm going to take as this one here. And I know the derivative of an exponential. I get the exponential back again, times the derivative of the exponent, in this case with respect to t. But we've calculated that partial with respect to t of minus theta vibration over t before, and it simply gets, one gets theta vibration over t squared. So this is the derivative of what I would consider the first function, and then times the second function, which is 1 over this quantity here. And then I have the first function, that was this, times the derivative of this 1 over 1 minus e to the minus the theta vibration. That's the derivative of the second function. And that is not too bad. It's to the minus 1, and so I pick up a minus sign here and then lower the exponent by 1, so I get 2. And then I have to take the derivative of everything that's inside here. 1 derivative with respect to t is just 0. And so I get this partial derivative here of this. I pick up this minus sign, and then I have to, because the derivative of an exponent is just the exponent back again, so this minus sign comes from this subtraction. And then I have to take the derivative of the exponent, which again is that same factor, which is the third theta vibration over t squared. So that's the way I would probably attack it. I can pull out lots of constants, and you'll notice I've got a theta vibration over t squared in both terms. So I pull that out and combine it with this term to get a theta vibration over t total quantity squared. And then I also have this factor, this exponential factor that I can pull out. So this one I pull out everything except for the 1 over 1 minus e to the minus theta vibration over t. And in the second term, I've got a minus, so that gives me a plus here. I pulled out this one, but I'm still left with this one here. So on top, I've got e to the minus vibration over t. And then on bottom, I've got the square of this. And then I simply put those over a common denominator, which the common denominator is the square. And to get this one with a square on the bottom, I just have to multiply top and bottom by the denominator. And when I multiply the top, I'll get 1 minus e to the minus theta vibration over t for this term over theta over this quantity squared. And then I have to add to that the numerator here, and these then will cancel. And so we're pretty much done. We get the specific heat, or the molar heat capacity, as just this quantity here. Or if you're looking at constant volume, and if you're looking at the heat capacity, the total heat capacity, then you'd multiply that times the number of moles that's present. And it's kind of an imposing looking formula. If you plot it, this is the vibrational specific heat formula. And if you plot that function, you get something that looks like this. I'm plotting it versus this reduced temperature. That's the temperature of the system divided by the characteristic vibrational temperature. If you look at it, it has some nice limits, namely at t equal to 0, it is 0, so it goes through the origin here. That's pretty easy to compute. We can do that. But the other one, as t gets very, very large, here, high temperatures, it goes to this constant r. And we can see that at high temperature, t goes to infinity, but this theta vibration over t is, this t gets large, is getting very small, so it's going towards 0. And so I can take our expression for the vibrational specific heat in this form, and let this quantity up here get very small, namely approaching 0. In fact, I'll let it equal 0 in the numerator, so e to the 0 becomes 1. In the denominator, I'm a little bit more careful in that I've got a 1 minus this, but I'll expand this exponential into a series here. And the first two terms are 1, the second term is minus theta vibration over t, the next one will be plus theta vibration over t squared, and so on. But these higher order terms, if this theta vibration is small, they get even smaller than that, and I get a cancellation here. And if I drop all these higher order terms and just keep the first term, which is theta vibration over t, then I square it and I get the theta vibration over t squared. And notice that exactly cancels with the one up here. And so in the limit, as t gets very large, this asymptotically, this specific heat vibration asymptotically goes to the value that's the ideal gas constant. For t equal to 0, t goes to 0, that's pretty easy too, because as t goes to 0, then this term becomes infinite. This one goes, as t goes to 0, it goes infinite as well, but the exponential dominates over this, and so ultimately the exponentials always win. And so this goes to 0 faster than this increases, and so the whole result becomes 0 on top. On bottom, again, as t goes to 0, this becomes infinite, and e to the minus infinity is 0. So indeed it does go through the origin here. And as I said, if you did a careful plot, it looks something like that for the system. one other thing that is sometimes useful is to just get the probability of an oscillator being in the level n equal to m. And that goes back to the original case where, remember, the probability is just this Boltzmann factor divided by the partition function, in this case just the vibrational. And I've got both of those. I know what the energy level is. It's or EM, because I'm looking at the nth one, is just this. And then I divide by what we've already found earlier as the vibrational partition function, which, if you remember, was this. You get a little bit of cancellation, and that this term here will cancel the 1/2 term up here. And I've written that out in some detail. And then this 1 minus will flip over to the top. And so you'll see this expression oftentimes. I almost never remember this. I just remember how to get to it from this expression and knowing what the vibrational partition function is. That gives you the probability that the oscillator is in the state where the nth state, where n is an integer. This is all dimensionless. And I think I've got actually a numerical problem that looks at some of this. We'll look at that here in a second.